So welcome back in the next series of next video of logistic regression. So we'll continue in the first lecture of logistic regression 1. We have discussed the foundation of logistic regression. Now we will discuss in this lecture series. We basically discuss the sigmoid function, how it is used. So the core of logistic regression is what? S-curve or sigmoid function. And what this function will do? This function will map the output between range of 0 and 1. Okay. So we'll take this function, that is rho of z. The function is rho of z equals to 1 upon 1 plus e to power minus z. Z is a linear combination of input features. Basically, this is an equation of a line or a plane, okay, hyperplane, or where x1, x2, xn are the features, and w0 to w1, w2, wn are the weights or the coefficients associated with that feature. So, the sigmoid function ensures that output represents probabilities. Okay. For example, if z tends to infinity, that the value of z that evaluates is a very large number, so then rho of z will reach to 1. Okay. Because of this minus power in this expression, let me use pen for you. So it is basically the function is rho upon z equals to 1 upon 1 plus e to the power minus z. So if the value of z increases, so this function can be rewritten as 1 upon 1 plus 1 to the power e to the power z. Obviously, if z is moving towards infinity, large number, it's a very large number. So what will happen? E to the power z will also approach towards infinity. So this fraction will be limited, or it will be moving towards its value, and that value tends to be 0. You keep on increasing the z, the value will be further closer to 0 and 0. So and that for at the extreme boundary, this would be actually 1 upon 1. So this is how the two large values are handled by S sigmoid function. Now what will happen if it approaches towards negative infinity? So what will happen is that this fraction, this particular fraction will be very large. So that means this fraction is large. So we have 1 upon, and this a number n, where n is actually going towards infinity. So what will happen? This number, the ratio will tend towards 0. Okay, obvious thing, simple maths. So then the output of z rho is 0. Now if z itself is 0, so e to the power 0, okay, it becomes 1. So it is 1 upon e to the power 0, that is basically 1 upon 1 plus e to the power 0, and that is 1 plus 1, and the probability is 1.5. So that is 0.5. Okay. So this is how the sigmoid function works. Let's clean it up. So logistic regression predicts the probabilities that are given by the input belonging to certain class. So this is what is a form of a sigmoid function, where this is the equation of line or hyperplane. Okay, line or hyperplane. Okay, so what we can write is y equals to, or let's say z, again remember these x are what? Features, and all w's are the coefficients. Okay, so this was our original function, sigmoid function. So what it will give? It will give the value of y for x. Okay, so we can test that what is the input that for a certain input, whether this y belongs to class 1 or it belongs to class 0. So if the values computed by this function sigmoid are near to 0.1, we can say, or it is above the threshold, we can say that yes, the it belongs to class 1. So the decision rule or the decision boundary, or you can say the threshold. Okay, so the threshold is over here is 0.5. So something above 0.5 will be termed as 1, and something below 0.5 will be termed as 0. Okay. Okay. So unlike logistic regression, what we have to do? We have to calculate log loss. And what is a log loss? And that can be explained as such as that, for example. So for a certain input xi, we compute the value. Okay? We compute the value. And then the output also by using the sigmoid function. Then we multiply this, so we get the probability of y belonging to certain class under certain input xi, and 1 minus yi is the probability of the probability that, but on certain inputs the class belongs to the other class, the value belongs to the other class. So we have this log loss formula. Okay, m is the number of samples. So here y is the actual level, because remember it is a supervised learning, so somebody has to give the levels, and this is your predicted value. This is your predicted value. Clear? So what will happen? These are the features, like say x1, x2 till xn, and you have a label y. So over here the output is given 1 0 1 1. Okay. Now you calculate by using the formula 1 upon 1 plus e to the power minus z y predicted. Okay. So by using the y predicted, you will have certain values. So once those values are found out, you can calculate the loss or the log loss. Okay. So log loss function ensures that the predicted probability is close to the actual class and loss is small. If the predicted probability is far from the actual class, the loss is large. So this is simple meaning. Okay. Now what our objective is? We have to minimize the log loss, the function j, and to compute or to adjust the log loss, we can use gradient descent to optimize the minimum possible loss. So for that we use the algorithm that is known as gradient descent, and in the gradient descent what happens is we have Wj, actually this formula is new, whatever the weights you are using, the new weights you will compute after first iteration. This is old minus alpha dot Jw upon partial derivative of Wj, and this is the index j. Okay, so it's a certain whatever I have written is a certain elaboration. The alpha is known as learning rate. This is known as learning rate. The only problem in this gradient descent, or the only difficulty or challenge, is that how to set the values of alpha. If alpha values are too high, then you can prematurely converge. If they are too low, then you have got very slow updation of weights, and you will converge at a very later stage. So you need lot of epochs. Okay. So alpha is the learning rate, and Jw, del of Jw divided by del of Wj is a partial derivative of the cost function log loss. And what the algorithm says, keep on repeating unless and until they converge. The gradient descent is not only the only algorithm. Okay, you can use stochastic gradient descent or the Adams optimizer also for faster conversion. There are many algorithms that can achieve the same effect. Okay. Now for multi-class logistic regression, what we can have, for more than 2 classes we extend the logistic regression to softmax. So instead of using single submit function, we use softmax function, and where we can say k is the number of classes, okay, and denominator ensures that probability is sum to 1. Now let's decode this formula. So let's say e to the power wt k x have been computed, okay, for all the inputs available for a class probability belonging to k. So y is k. So k can take various values in the range. Like suppose that we have 0 to 1 is the maximum range of the probability. So we can divide something below an interval, let's say 0.2 is termed to be class 0. Something above from 0.2 to let's say 0.4 belongs to class 1, and from 0 to 6 belongs to class 2, and this belongs to class 3. So what we have done, we have taken the certain divisions of the interval, and what this is calculating the value of all inputs, okay, that belongs to class k, and class k, or if we can have 0 or 1 class. So the values of entire interval is being calculated over here. Then the value of this entire interval will be calculated, the entire interval and this entire interval. So what we'll have, we will have e to the power w 0 t x plus e to the power w1 t x plus e to the power w2 t x plus e to the power w3 t X. So we have 4 classes. We have calculated the value and we will sum them up. When we sum up, we achieve this expression. Okay. So that is forms our denominator, and then we will take individual values, and we will find the ratios. So this will ensure that probability sum up to 1 only. Okay. Now, there can be 2 possibilities. One possibility is that we are overfitting the values or we are underfitting the values. So, to control the overfitting and underfitting, what we do? We use regularization, and we can use L2, that is ridge regression, or we can do L1 lasso. Okay, so what they do is they introduce a certain variable or certain weights that penalize. Let me get the pen for you, then we'll continue. So in L2, what happens? The large weights are penalized, and that is we prevent overfitting. Overfitting means that the algorithm was applied to on a data set, and yet the algorithm learned the data set very well, but it will perform badly. It will perform badly when it sees a certain unforeseen data. So in that case, that we call it overfitting. Okay. Okay. So that is overfitting. And L1 regularization, what it does? It leads to the feature selection by shrinking some weights to 0. Okay. So what it does? The difference is the lambda is to be calculated. Then you sum up all the weights and square them in L2. And in L1, what you take? You take the mod of weights and add them up and multiply with the lambda. So this prevents, this lambda will be calculated in such a way that certain weights are summed to 0, and over here in L2 you prevent the large weights from becoming overfit. Okay, so this is how you reduce the overfitting. Clear? So that is the extension that can be used in the logistic regression to prevent overfitting. Okay. Now there is a certain matrix involved. When you are applying a model, you should also calculate how the model is behaving. So for that, we have accuracy, the first matrix in which you should be interested in, that is accuracy. And accuracy means the percentage of correctly classified instances. Okay. Precision is what? A true positive, okay, divided by true positive by false positive. Focuses on positive prediction. The recall is what? Sensitivity. Okay, how, and that tells the imbalance data. If imbalanced data set is there, so this becomes sensitive, becomes very important. Now how it can become imbalanced? For example, let's say there are 2 kinds of political party. Okay, A and B, for simplicity. And there is a certain geographical region that belongs purely to A, and there is a certain geographical region that belongs to B. Now, if the number of samples collected in the data set are mainly focused from the region A, and some of the samples are collected from region B. So obviously in this data set favors that A will be the winner in the election, incoming election. But actually it can be different. Okay. So this what we call as imbalanced data set. You are giving more importance weightage to A than B. So F1 score is the score that is in which you should be interested, because this takes care of everything. And what is done? It is simply a harmonic mean of precision and recall. Then we have ROC curve that shows the trade-off between true positive rate and false positive rate. How the algorithm did the trade-off. And AUC measures the classifier's ability to distinguish classes. Okay? So applications of logistic regression. Medical diagnostic, you can predict whether your patient is suffering from disease or not. Fraud detections like fraud transactions, okay, the cyber frauds. Marketing, you can predict the conversion, customer conversion, okay, the target class, etc. Spam detection, you can filter out your emails, and credit scoring, determining the loan approval. So these are the various applications. I've listed only few, but you can extend it. But always remember that you can use logistic regression in a situation where the output is between 1 and 0. Okay? Yes and no. Or you want a probabilistic prediction between the range of 0 and 1. And if you have more than one class to predict, you can use softmax function. Okay. So logistic regression is a simple but yet powerful classification algorithm. It provides probabilistic predictions, making it interpretable. Regularization, L1 and L2 techniques prevent overfitting. It works well for binary and multi-class classification via softmax. Suitable for problems where the relationships are linear in log odds space. One assumptions. So, thank you everyone. This finishes the logistic regression part 2.